Hi everybody, and welcome to exercise 3 on page 9. Okay, and this is an exercise that I'm hoping that you've given a try to. It's a pretty challenging exercise, so if you don't feel bad if you struggled with this is not an easy thing to do, matching graphs to functions to contour plots. Okay, but by doing it, we can gain a lot of insight into how functions of two variables behave. Okay, so this is not going to be a complete solution to this problem, but it's going to maybe give you some ideas as to how you might proceed. If you were stuck on getting started on this problem, it might give you some ideas of how you can continue in going about finishing the problem. All right, there are different ways of doing a problem like this, but I'm going to share with you a strategy that I find helpful. Okay, so I think it's difficult in general to match formulas to contour plots. Okay, and so here's the method that I'm going to propose. I'd like to first see if we can match some of these formulas that we have on the first page with, or I'm sorry, no, I want to do it the other way. I want to see if we can start with the contour plots and match some of those to the graphs that go on the next page. That I find an easier way to start the problem. We'll ignore the formulas for now and just think about contour plots and graphs. All right, so let's maybe just pick one to get us started. Okay, remember that a contour plot is about taking a slice through our surface where z is constant. So kind of at a constant height, we're going to take a slice through our surface. And just to pull one of these out of the air, I'm going to look at number 6 down here. Okay, so as you look at the graphs on the next page, do you see a graph that looks like if you were to slice through it using a horizontal plane, you would get a bunch of circles kind of in pairs of 4, if that makes any sense? Okay, if you kind of take a glance at these graphs, this one looks promising because if you took a constant value of z and sliced through this surface, you're going to kind of get a circle for every one of these peaks that you see here. Okay, so that's some pretty good evidence then that surface D actually goes with contour plot 6 on the previous page. Okay, and we'll go up and match 6 with D up here. Okay, so that seems promising. That match looks to be reasonable from what we're seeing. Okay, and another thing we might notice here is that there are a lot of our contour plots that involve circles. Okay, for instance, this one, number 1, number 3, number 5, and number 4 and number 5, they all involve circles somehow. Okay, so if you look at the graphs, which of those graphs look like you would get circles if you took horizontal planes and intersected them? Okay, well, I'm seeing circular slices for B, C, F, and E. Okay, so those seem to be the 4 graphs that would go with the 4 contour plots that we checked on the previous page. How do we know which is which? All right, well, let's go back to the contour plots for a minute. Okay, maybe pick on number 4 here. Notice that those contours are equally spaced. What does it mean for contours to be equally spaced? Remember the discussion that we had a couple of pages ago? So equally spaced contours means that the steepness of our surface is constant. Constant steepness. Okay, so as you look at the 4 graphs that we checked on the previous page, which one of those 4 looks like the steepness stays the same? Okay, to me, it looks like this cone-shaped thing. If you draw a line, notice that that line has a constant slope. Okay, so that's pretty good evidence then that C must go with contour 4. That was the one where we had the equally spaced circles. Okay, and we'll go up here and match 4 with C. Okay, if you contrast that behavior maybe with what's going on up here in number 1, those are also circles, but they get closer together as we get farther away from the origin, so that's kind of telling us that whatever surface this matches, it's going to be steeper away from the origin. Which one of the graphs does that behavior match? Okay, well, steeper away from the origin, that seems to match F here. If you were an ant walking on the surface, notice as you get away from the origin, you're getting steeper. So F appears to match contour plot number 1, okay, because of that steepness behavior. Okay, we could go up here and match that with capital F. All right, so you kind of get the idea of maybe just a few things that you might try when you're trying to match contour plots to graphs. Okay, and I'll let you see if you can take it from there with this part. All right, and now let's talk a little bit about the other part of the match. Okay, so what could we do to match formulas to graphs? Okay, and just so that we've got a little bit more writing space, I'm going to be switching back and forth between a couple of pages. Okay, so you can see your graphs here on this page. And what I've done is to create the other page, I've just made the graphs a little bit smaller so that we've got some room up at the top to write. All right, so I'd like to pick on one of the formulas from the previous page. Okay, I'm going to choose the formula that went with little f on the previous page, and that looked like f of xy equals cosine of xy over 3. Could we find a match for that among the graphs that we have below? Okay, well, the cosine function has kind of an interesting property, and that is that if you take the cosine of 0, you get 1. And so we can use that observation to notice that if we plug in either 0 for x or y, what's going to happen is that the inside of our cosine function, the xy over 3, is going to turn into a 0, and out is going to pop the number 1. What is that saying? Well, it's saying that whatever graph matches this formula, it's going to have a z-value of 1 everywhere that x is equal to 0 or y is equal to 0. Okay, so can we find a graph that matches that behavior down below? Well, notice A seems like a pretty likely candidate. Here's the number 1, and notice that we're up at that number 1 everywhere that y is equal to 0 and everywhere that x is equal to 0. Okay, so that seems to be a perfect match for formula little f. Okay, cosine of xy over 3. All right, let's get rid of our writing here, and I'll warn you, I'll be doing some erasing. Okay, there's not a whole lot of space here. So you can, if I'm going too fast, you can pause the video or rewind it if you want to. All right, let's pick a different formula and see if we can come up with a match for it. I'm going to pick on formula b this time. X squared plus y squared. All right, so what tools do we have for analyzing the behavior of functions or formulas? Well, you might remember we have cross sections and contours. I'm going to start with contours, which involves taking the z value and setting it equal to a constant. C equals x squared plus y squared. What is that the equation of? Okay, well, we've seen this before. This is a circle, so the contours are circles. All right, so we're looking for a graph that has circular contours, and there are 4 of those. We've already seen those before. I'm going to check them again. So it's got to be one of those 4 that I'm checking. All right, and to decide which it is, we could maybe dig a little bit deeper by looking at a couple of cross sections. So 0 are nice values for x and y. I'm going to choose to just plug in 0 for both of those. And I'm just choosing 0 because it happens to be a nice number. We could also choose another number. Okay, so f of 0y means we're going to plug in 0 for x, so we'll get 0 squared plus y squared. That's just y squared. And so what we get is z equals y squared. Notice that that's a parabola. Okay, and down here, we're going to get x squared plus 0 squared is x squared. That's also a parabola. So if we take cross-sectional slices of our surface, we should get parabolas. And the question is, which graph matches this behavior? Okay, well, notice that f down here is kind of a nice match. Okay, because when x is 0, notice Okay, my drawing skills, again, are not the greatest, but you can kind of see the parabola there. Okay, and then when y is equal to 0, we get a parabola that kind of looks like that. Okay, so that looks like a pretty good match for, let's see, what was that formula number B? Okay, let's maybe do one more together. Okay, so again, we'll get rid of this. Okay, and I'm going to pick f of xy equals 4 over x squared plus y squared. Okay, now we could use an analysis of cross sections or contours again. Let's maybe start with cross sections where we make c the z value equal to a constant. We take this equation and just play with it a little bit. We could multiply both sides by x squared plus y squared. And then I'm going to get the x squared plus y squared by itself. So x squared plus y squared is 4 over c, and notice that 4 over c is just a constant. If you think of it all together, this is really the equation of a circle. Okay, so this is going to be one of those 4 graphs that we checked below, okay, that have circular cross sections. And we kind of have already found a match for this one, so that means it has to come down to one of these 3 that we're looking at here. Which of those 3 might it be? Okay, well, there are different ways to come to this conclusion, but one way is to just notice the general behavior of our function. Notice that this fraction is going to be large when x and y are small because of the fact that the smaller the denominator is, the bigger the fraction is. Okay, so let me try to put that into words this way. We're going to get large z values near the origin. Okay, because that denominator is small. If you think about it, that's a match to the behavior of graph B. You can kind of see that if you put yourself on the surface and you get closer to the origin, z is going off to infinity. It's getting really, really big. It's like we have an asymptote there. Okay, and that's a way of kind of pinning down the fact that B goes with little c, formula little c. Okay, so again, that's not a complete solution, but it might give you some ideas of different things that you can try to make these matches. So I'd encourage you to try to finish this problem and realize that there's not just one way to do this. Okay, there are all kinds of different ways that you can make these matches. Okay, so be creative, and when you're done, you can take a look at the written solutions and compare.